So we're going to conclude this portion of the class, this week 5, with the discussion of unsupervised learning. Supervised learning is where the model learns from labeled data. Unsupervised learning is where the data have no labels. We're trying to find hidden patterns. We're trying to group observations. We're trying to figure out the underlying structure of the data. So this is common for clustering, anomaly detection, and market segmentation. Because for segmentation, we group customers by behavior or preferences. Document grouping, this is pretty common in natural language processing where we automatically sort news articles or research papers. Image compression groups similar colors or patterns, and then anomaly detection find fraud. Equipment failure, unusual behavior. Clustering helps uncover structure where labels are missing. Popular clustering algorithm for grouping data into k-clusters is k-means. Basically, you assign each point to the nearest cluster center, and then you update the cluster. It's simple and fast, but it's really effective for getting that first pass of the data. In k-means, you don't necessarily have to assume that the clusters are roughly spherical and equal size. They could be any size. In fact, clusters will be larger or smaller based on the structure of your data. So here's some k-means visualization. As you can see, the cluster is not necessarily the same size. So the idea of k-means is that given n data points and d dimensions, you split them into k clusters, and this minimizes the total distance from each point to its cluster center. So argmin underscore s, x minus mu squared. You're minimizing the total variance within the cluster. So you initialize, you choose k random points as starting centers. You assign each point to the nearest center. You update by recalculating each cluster center as the mean, and you repeat until the clusters stop changing or the total error stops decreasing. This always converges, but it has different results based on where it starts. So it always stops, but it may not find the best clustering, which is why you should run a number of different clusters with this algorithm. It's sensitive to initial center, and it's sensitive to outliers. So if you want to run it with multiple times and choose the best result and try different initializations. K-medoids is like k-means, except you choose k data points as medoids. Each point joins the cluster of the nearest medoid. You try swapping each medoid with each non-medoid point. If swap reduces total cost, accept it. Continue to do this until termination. Repeat the assignment plus update steps, and if cost stops decreasing, terminate. Cost is the total distance between all points that are assigned medoids, and it's more robust to outliers because it minimizes pairwise distance, not variance. You can choose the number k by running clustering for different values and looking for the elbow. So basically the point where you stop getting improvement from additional clusters. You can't just increase k, because if you increase k to the size of your data set, you'll end up with a 0 error. Which might sound good, but you don't learn anything from that. So k-means, you take the mean of points, k-medoid is the actual data point. K-means, you do the sum of square distances. K-medoid is the sum of pairwise distances. K-medoid is less sensitive to outliers and easier to interpret, but it's a lot slower in terms of computation because taking the median is a more expensive operation. So unsupervised learning helps find the structure within data without labels. Clustering is a key tool, grouping similar data points. K-means minimizes variance to using cluster means, and K-medoids minimizes pairwise distance using real data points. Choosing the right number of clusters is important using the elbow method. Thank you, and we'll see you next time.